The first speaker this afternoon is Professor Kinser from University of ICRA. The title of his lecture is K-polynomials on type A orbital quivers and lacing diagrams. So please.
Thank you. Is this audible? Speaking. Do I need to speak louder into it? Or are we good? All right. Thank you. So thank you everyone for coming. Thanks particularly to the organizers for all their work into putting into this conference and for letting me speak here. Really appreciate it. I can say this is my title. I have a better marker for my collaborators. This is joint work with Alan Knudsen, who's at Cornell University, and Jenna Radshot, who is now at University of Saskatchewan and was formerly at University of Michigan. And so let me do some. So please let me know, as with other people, if I'm not writing large enough, not dark enough. Just feel free to interrupt me anytime. So first I'll do a setup and notation. These things are kind of standard, just to make sure we're clear. K is a field. Q is going to be a quiver. As usual, we'll have vertices Q0, arrows Q1. And I'll denote, if I have an arrow A, you denote its source by SA and its target by TA. And this stuff I keep a little longer. D is, for the whole talk, D underline is a dimension vector. And today we're going to be concerned with, this is more in the realm of algebraic geometry and commutative algebra. It connects with type A quivers. And we're going to be studying some varieties built from matrix spaces, matrix varieties. So I'm going to denote by mat M cross M, the variety of M by N matrices over K. And of course, as a variety, it's not very interesting by itself. It's just symbolic to a big affine space. But we're always taking it with its natural action of GLM cross GLN action. Multiplication on the left and right by invertible matrices. Okay, so that's the basic ingredients here. And the actual thing we want to study are, for a fixed Q and D, we're going to study the representation variety of a quiver. So let's say fixed Q and D. And I'll leave this up just to remind us of the definitions. The representation variety RD is you take the product over all the arrows of the matrix spaces whose sizes are determined by the dimension vector you fix. So that would be mat D of the source of A by D of the target of A. And yes, this is correct. My matrices act on the vectors on the right, on row vectors on the right, so I do want to do it like this. And the group that's acting on this variety, then once we product all those together, is, well, the base change in each vertex, base change group in each vertex product together. So we take the product over vertices of GL DZ. And so that's the representation variety. And this is base change group. Okay, and just by the definition of the setup, what does it mean for two? So points of this are representations. Points of this are just throw some matrices over each arrow of your quiver. So points of this are by definition representations of your quiver, but of course we have many matrix representations of the same, what we call the same or isomorphic representations of a quiver. And when are two things isomorphic? Exactly when you can change basis to make them equal. So just basically by the definitions, we have a bijection between the GD orbits in the representation variety and ISO classes of reps of Q of dimension vector D. So it's kind of like, geometrically encoding the way we think about quiver representations is for a fixed dimension vector. You have a variety parameterizing them, but with some redundancy because you have parameterizing them with fixed choice of basis. And then the base change group gives you orbits that let's see which way do I want to do this. Okay. Gives you orbits in bijection with isomorphism classes. And we're specifically interested in, so the orbits are maybe not so interesting in themselves because they're always smooth. They're interesting in the orbit closures as varieties. And let me give you some, so that's a definition, a precise definition of what we study. But where do these things arise in other parts of mathematics besides just making this definition? So today I'm interested in quiver orbit closures. And I would say they arise naturally in several places. Well, say the first one is obvious, representation theory of quivers. There. And even if you stay in this realm, there's many beautiful connections between what's going on with the geometry of the orbit closures and what we think of as more algebraic things like short exact sequences in the category and so-called X and Hom orders on representation. So there's already, if you stay in this world, there's many interesting connections between the geometry and the representation theory. I decided I'm not going to try to list a bunch of names of people because it's such a large audience. I'm sure I would leave numerous people out if I tried to list names. There's some very nice surveys where I will refer to you more information on this. So that's one place it arises. Lie theory, these things, quiver orbit closures come up in Lie theory. Again, some examples, you can use kind of constructible functions on these to realize certain enveloping algebras as convolution algebras. This goes back to many work of many people, including Lustig and Ringel, and there's recent work by Geis, Leclerc, and Schur. And so there's some ways you can get some interesting constructions in Lie theory by studying these orbit closures. They come up in algebraic geometry, and even really independent of thinking of any representations. This might be a little less well known here. I'll at least say one more sentence. And specifically in the theory of vector bundle degeneracy loci. So this is maybe initiated by, well, it goes back to this classical Tom Portes formula, where there's this idea of incorporating quivers into it. Goes back to Brooke and Fulton in the late 90s. And then finally, commutative algebra. So this is field of algebra where you assume all elements in your ring commute. It may seem like a strange condition to many people in this room. But I assure you there are many natural examples, actually. So. And where does this come here? Like, you can think of this as generalizations of determinantal varieties. And that's not clear from the definition how there's any determinants or anything. I will not go into that in detail, but maybe make some remarks at the end if time. All right, so that's overall, maybe a little bit of big picture to where quiver orbit closures appear in parts of mathematics. Today I'm going to focus on a very specific small part of the story. I decided to try to focus on, basically just try to tell one story today, not everything that I think is interesting about these and about the work I did with Alan and Jenna. So I'm going to limit myself to the following. I want to try to explain how so-called lacing diagrams which appeared, at least the first, I'm sure many actually people have thought about type A quiver representations kind of invented lacing diagrams. And the first place I've seen in the literature is in the work of Algebras and Delfra in the early 80s, so that's in the representation theory quiver side, I guess. So this is like 80s, 1980s or earlier. How these ended up appearing very naturally in recent problems that arose in 3 and 4 in people working in algebraic geometry, usually algebra side. So recent, I mean like 2000s and later. And so as a general warning, I'm not doing any, really the problems are, I'm using this tool that many of you have seen in representation theory. Really the problems are coming from algebraic geometry, commutative algebra. I'm not doing any deep type A quiver representations today. Everything is really, the problems are more in algebra and geometry, algebraic geometry and commutative algebra side. And so let's see. So I need to define these lacing diagrams here. So basically close this. So the goal here, basically an outline, I'll try to define these lacing diagrams carefully, but maybe give you some additional way of thinking about them that came from 3 and 4, and try to state this formula we came up with for the K-polynomials of orbit closures for type A, and I'll explain what a K-polynomial is just briefly. All right, so let's do, let's explain lacing diagrams. So we're going to fix always a quiver and dimension vector. And a lacing diagram is it's essentially just a columns of dots connected by arrows. And I'm going to define it more by example. I'll give you a precise definition after the example. I'm going to do the example first. And these do take a little bit of time to draw. So, let's see here. Let's start. Take advantage of a trick I believe I learned from one of my postdoc mentors, Ralph Schiffler. To give you an example. So I'll give you a second, I'll talk if anyone wants to copy it down or take a photo or something. So these are lacing diagrams for the quiver. Oh, I was supposed to draw the quiver first. Oops. So the quiver here is just like this type A quiver. And the dimension vector is 2, 3, 2, 2, 1. So what's going on with these lacing diagrams? My dimension vector is 2, 3, 2, 2, 1. So in the columns I have 2, 3, 2, 2, 1 dots. 2, 3, 2, 2, 1 dots. And then they're connected by arrows, but you can't just connect them in any crazy way. For a lacing diagram, you want it, for every dot, you can only have one arrow coming out on each side. So is the idea clear without me writing out full sentences here? That's the idea. And this is probably the normal way. If you work with type A quiver representations, you probably visualize the indecomposables, right? So you can think of this then as, well, if I decompose this, how would I take this and think of a type A quiver representation? I would take an indecomposable that stretches from one end to the other, another that only goes from here to here, and I direct sum them together. Same thing over here. So these lacing diagrams are ways of visualizing type A quiver representations. And Algebras and Delfra used them to study the degeneration order, the orbit closure order in these varieties, and to show how it connected to Hom spaces, dimensions of Hom spaces. That was their motivation for introducing them. Now in early 2000s, Knudsen-Miller and Shimozono kind of reinterpreted these in a way that's more natural for in the world of like combinatorial commutative algebra. As you can think of a lacing diagram. Write this down. You can think of the lacing diagram as actually interpreting as encoding a sequence of partial permutations, which I've written below them, and that I'll write down here. Yes? Could you say it again?
I try to copy this, but my pencil refuses.
Why is that?
Just matrix. Should it be the 2 by 3?
No, maybe I said this quickly earlier. My matrices act on row vectors on the right, so we use right. Yeah.
Should it be 3 by 2?
Let me give a quick answer. I don't want to explain the conventions of. Let me write a sentence here. The conventions of exactly how you encode this and this depends on the orientation, and it kind of flips with the orientations of arrows. There's a number of like awful conventions to get right that I basically don't want to explain in the talk. What's that?
Square matrix, there's 2 dots, 3 dots.
Oh, do I have like a really? Oh, yeah, how do I do that? That is definitely a problem. Sorry, I see what you're saying. I thought you were okay, let me think about this for a second. How did I write that down wrong? I think I just need a column of zeros. I'm sorry. Let me say what I was saying anyways, which is the exact convention of how you do these things is a little painful. We do definitely need this to be 2 by 3, I believe. So this should, yeah. So there should be. This the top one goes to the top there, so there should be 2 more zeros. Thank you, Marcus. Thank you.
There are too many ones.
Oh, this one's also just clearly.
No, because the other goes up.
Is that better?
No.
First and third columns. Is it better? Oh, I see what you're saying then. This is 2 by 3. Well, let me say it this way. I'm not going to do any specific computations that require me to. I'm sorry. I must have like just copied something wrong here. It could probably be fixed in 5 minutes. Others been talking about it. Thank you. So let's see. So what happens here? Yeah, I think this is okay. So let me write that in a sentence. So a lacing diagram, the key idea is lacing diagrams can be reinterpreted as sequences of partial permutation matrices. Oh, I might have written that over. Yeah. So lacing diagram is just a sequence of partial permutation matrix. What is a partial permutation matrix? It's just a submatrix of a permutation matrix. You can have at most one each row and column, the rest zeros, but you don't necessarily have to make it square. And yeah, and by slight abuse of notation, since they encode exactly the same data, we also just call this a lacing diagram. So either of these ways of encoding it, the same mathematical concept, we're going to call it a lacing diagram for short, rather than every time saying sequence associated to a lacing diagram. Okay, so let's see. Yeah, so first thing to notice, well, lacing diagrams, now you can kind of see precisely how they give you a quiver representation. So note that I kind of said quickly, but now that once we have a matrices associated to them, you can note that each lacing diagram really is a point of the representation variety, right? It's a matrix of the appropriate size associated to each arrow. So each point of the lacing diagram, now that at least gives you like a more rigorous definition of how the diagram encodes the representation. And of course, many of them will be isomorphic. So if this is W1 and W2, so these are just 2 different lacing diagrams encoding the same representation of the isomorphism, but they're different points of the representation variety. So the thing is, you might look at these and say, well, what we're going to be interested in is like the number of crossings and stuff are going to encode some information. And these might look different at first because this one does not cross and this one does. But I claim that if we interpret these in the right way, these actually cross the same number of times. The problem is some of the crossings are kind of hidden. So I'll make a definition. If you have a lacing diagram W, CW is the completion to a sequence of honest permutations matrices. So how do I complete these? Well, you actually have two choices. You can either fill it in from the, you can either start filling things into the bottom right or top left. Actually, you can do it many ways. Of minimal length. Say that. So minimal length in the sense of a permutation as a Coxeter length. And again, like I said, you can either kind of complete it to the left, down and to the right, or up and to the left. You have some options here. There's conventions that depend on the orientation. I'm going to avoid explaining these in this talk because it's very confusing. But there's a convention depending on the orientation of which way we fill it in. It's actually pretty easy to see with the lacing diagram. I've drawn these with a certain alignment. You might ask why I kind of went zigzagged up and down. Well, these are aligned at the bottom, so I'm going to complete this now to like having a bijection between the dots. So I'm going to complete that like that. This corresponds to making this into a full permutation this way. This one's already an honest permutation. This one, these are aligned at the bottom, so I'm going to complete it at the top. That corresponds to filling this in like this. Adding stuff onwards and so forth. And then this I fill in like that. It corresponds to filling like that. So is this idea clear? So we're completing all these to honest permutation matrices in a way that depends on the orientation. And so here we have that. Let's do this one too. So now we see these are actually both have the same number of crossings when we complete it the full way. And so you take the completions of minimal length, but given however you started, if you start with something with a bunch of unnecessary crossings, zigzagging up and down, you might really get a lot of crossings in. So the next definition is a minimal lacing diagram. If what we're going to call the length of W, which takes into account this additional completion, is defined as the number of crossings of the completed diagram. Is minimal among W prime isomorphic to W. So if you look at all the different lacing diagrams that would give you the same isomorphic representation, and you complete them all, check the number of crossings, whichever ones have the smallest possible. It's not unique, there's probably many of them or somewhere, but if they have the smallest amount of possible, then it's called a minimal lacing diagram. So that's the definition we use. I'll give you one that maybe many people in this audience might like a little more. Another way to say this, there's actually several other ways to say it. Say a more geometric one first. This will be the same. This should equal the codimension of the GD orbit of W. So if the number of crossings equals the codimension of the orbit, then it's minimal. And generally, you can get more. Another equivalent way, which we might like here, if the number of crossings is the dimension of the space of self-extensions of it, thought of as a representation. And X makes sense because this is a representation. So I can take its space of self-extensions, which just tells you the codimension of the orbit here. And if that's equal to the number of crossings, that's the minimal possible, and that's what makes it a minimal lacing diagram. And so these are both examples of minimal. I didn't even make an example of not minimal one, because you can just quickly just make a bunch of things cross unnecessarily and you get something that's not minimal. All right, so let's go back up. So this idea of minimal lacing diagrams, I believe, is original to Knudsen and Miller and Shimazano, and it maybe you think, why do I care about this from a representation theory standpoint? It really comes more from the geometry. And I'll tell you a little bit about why they're special later. All right, so fact is that all minimal lacing diagrams are, once you find one, so for example, compute the space of self-extinctions, if they are quiver or something, and you kind of just find one minimal one, you can get all of them from one by a series of moves of just pushing the crossings around. So all minimal lacing diagrams for a given orbit are related by moves that look like the following. If I have a crossing on the right, I can exchange with a crossing on the left. And there's some minor technicalities here that I don't want to get into. You have to I'll say it out loud, but I don't want to write it all down. These all basically each you can't have it like two dots on the outside or these virtual extra added dots. Otherwise, that'll add some unnecessary crossings. But as long as at least one dot on each outside is not an added one, is really one of the original ones, and both of them in the middle have to be original ones, then you can use these moves, and you can go from any one lacing diagram to another, any one minimal one to another. Now we have another kind of move that's maybe less natural, because it changes the orbits, but it's important in computing K-polynomials. We're going to call these a K-lacing diagram. For an orbit. Is one obtained from minimal diagrams. By those moves, previous moves, along with, we can also do this kind of K-theoretic move, which is a little strange. I'll draw it, is just to basically overlay them and take the most crossings. Put this in a different color. So you got moves, you've got crossing, crossing, and here I will write the caveat because it's a little more important, is middle two dots must be consecutive. So that's a K diagram. This spins a little strange. The warning here is this can change the orbit. This doesn't keep you in the same orbit. Kind of clear if you just think of type A quiver representations, how you draw the strings. Moving the crossing around doesn't change the isomorphism class of representation. This will, because you can add, you can kind of undo or add new things. So this changes the orbit. Can change orbit. So I'll use these to modify these examples. Like for example, these guys cross here. I could move this crossing here and get another minimal one, or I can add both of these crossings, and then that's a K-theoretic diagram for this one. Or kind of even, but this one happens just by kind of coincidence to give you the same isomorphism class. You still have a long lace, and you have one going from here to here. You could also do something like in this one. Let's see which one's still there. There are many options at the point. This one I wanted to say, yeah. So these two, if I look at these two, the things coming into them are crossing here, but they're not crossing there. So instead of pushing this crossing over, I can just make it cross. And then if you look at this picture, you see you've actually changed the isomorphism class. You've kind of taken this indecomposable that went from there to there, and you've split it into two. because this is like a red, this would be red now. That's maybe less natural if you're thinking in terms of representations. I'll try to give you an idea later where it comes from, but I wanted to at least give a precise definition. All right, so I'm going to pause for a second. That's all I want to say about lacing diagrams. I wanted to try to go carefully and slowly and give a precise definition. I'm going to next talk about K-polynomials, but I'm happy to take any questions if anything was unclear. Lacing diagrams. So you believe these are kind of natural thing to look at for type A quivers. All right. Let's see. Here. So the point is, these are going to be useful into developing. Where we're going from here is I'm going to tell you what a K-polynomial is. Maybe not everyone knows what a K-polynomial of a variety is. And no, it's just an invariant. It's like varieties can be complicated mathematical objects, and a K-polynomial is just an invariant. And then I'm going to tell you how these not only are useful in coming up with a formula, but I'll try to give you an idea of how they naturally arise, really from the geometry itself, how these minimal lacing diagrams come from the geometry itself. So, yeah, what's a K-polynomial? As always, feel free to, if you want a little more detail, I'm going to give a brief, really brief but rigorous definition, kind of crash course. If you want more detail, I'm happy to clarify anything. The setup is that we have a torus action on just affine space for now. So let's say like our torus is K-E, acting on A-N. And then we have a T-stable subvariety. And when you have a torus action on a geometric object, then you get a multigrading. I'll probably just call it grading. It's in commutative algebras called multigrading. Sometimes emphasized it's not just a grading by the integers, but it's a grading by the character group of the torus. So you get a ZE grading of the coordinate ring. In the normal way, where you break it down into weight spaces of your torus action. And then once you have a grading, you can count the dimensions of each piece, and you get Hilbert series. Again, sometimes they call it the multigraded Hilbert series, but it depends on what grading you're using. I'm just going to write Hilbert series for short. So H. And this is just a generating series, kind of a power series and formal variables corresponding to a basis of this character group here, where the coefficients encode the dimensions of the graded spaces. So normal Hilbert series, like you know for a graded ring, but we have more variables to take into account that the grading is fancier. So that's the Hilbert series, and then we define the K-polynomial. And the set at the left, the K-polynomial of V is, I'm going to denote it by brackets around V, and it's just the ratio of the Hilbert series of the coordinate ring of V itself with the Hilbert series of the ambient space. Okay, so that's kind of quick and dirty definition of it. If you're coming, maybe you think, where does the letter K come from? Well, another way you could think about it is you could look at kind of the category of ZE graded modules over this polynomial, over the coordinate ring of this affine space, a polynomial ring, and then you can look in the Grothendieck group of this category of graded modules, and this will represent the class in the Grothendieck. So that's where the K comes from. It really is like a class in a certain Grothendieck group. But you can by choosing some coordinates like we've done on our torus, then we get a nice representation actually as a polynomial. Okay, one lie about the K-polynomials is it's not an honest polynomial, it's a Laurent polynomial. Oh, I wanted to write down the thing I said. So it's kind of the K class in the category of Z E-graded modules over the polynomial ring. And it's always a Laurent polynomial. In our setup, I should say, we're really using some facts. There's some kind of maybe hidden assumptions on the grading, but in most good cases, like we have here, like only the constants in degree 0, then it's actually a Laurent polynomial. Everything is finitely generated because we're working over finitely generated modules over this polynomial ring. And I'll say, like, maybe if you think this is a little, when you think about things, you do at least have a bijection. What is this going to correspond back to in the lacing diagram is that the variables that you're working with here of this polynomial are just in bijection with the dots of the diagram. So that's when you're actually doing examples and computing it, the variables of this polynomial are in bijection with the dots of your lacing diagram. So we have our dimension and everything fixed. Well, okay, what I'm writing here is for the application to the quiver. I gave you a general definition. This is what it's going to be for us. So it's somehow a little more concrete. Close to being able to state this formula, I'm going to do one. I'm going to say example in quotes. It's not really like a very thorough example here, but it's basically an example definition to introduce the last ingredient I need to state our main theorem. So to each permutation, we're going to be mainly interested in varieties coming from combinatorics. So to each permutation, we have a so-called matrix Schubert variety. Which is just by XW. And this is just the BWB orbit closure in space of n by n matrices. Again, you maybe want to know which B I mean here. I mean, it depends on upper or triangular. We're going to apply it in several settings where these can be different combinations of upper and lower triangular matrices depending on the orientation of quivers. So again, I'm not going to be really detailed here. There's many variations depending on what you take, but let's just leave it like that. They all just amount to changes of variables in your polynomial ring. And so the definition I'm making here is we take this is a variety. We have a torus action on it by left and right, two n-dimensional torus acting left and right, and then we get the double Grothendieck polynomial. I'm going to just define as the K polynomial of this matrix Schubert variety. And so the formula I'm about to state, or kind of our main theorem, is going to be in terms of these. Now, what are these double Grothendieck polynomials? I'm not going to, just obviously due to time constraints, I'm not going to write a bunch of examples or calculate up there. I do want to mention though that these have nice recursive formulas. There's many formulas for where they originated from is they have nice recursive formulas due to Lascaux and Schützenberger. Which I think I wrote down 1982. So these have been studied a long time because Schubert varieties are kind of a classical thing. And they have the recursive formula. So in principle, there's many other formulas. So these are like really computable polynomials in purely combinatorial ways. And so what we're going to do is how they're going to be playing I want to just slightly extend really introduce a notation for how we're going to use them to study this quiver orbit closure thing. Is we're going to let, if I have a lacing diagram W1 up to Wn, I'm going to define kind of a Grothendieck polynomial associated with that lacing diagram by just taking the product of the Grothendieck polynomials of these individual permutations. So this is after these are really partial permutations, and we just leap into honest permutations and use this definition. All right. Yeah, there's different sets of variables which I'm intentionally avoiding writing this right, because there's kind of a lot of conventions to get right, and how we're actually going to apply it to this right. Good point. They're kind of overlapping set of variables. There's kind of one set of variables on each end of each arrow associated to each column of dots. So each factor has some overlapping sets of variables with each other factor, but also some units. Okay. So now I can state our formula name here. And then I will just say, I won't even say I'm going to talk about the proof. I'll talk about some ingredients that go into the proof, because it's a very fun project that uses like a lot of different things. I'll try to just at least mention some buzzwords of some of the technology we use. Here's me state the theorem. So this is like I said, the joint work with Radschott and Knudsen and Radschott. It says if you have omega in the representation variety, a orbit closure of codimension C, then its K-polynomial of that orbit closure is equal to the alternating sum of lacing diagrams, where the sign is determined by how far, remember the minimal number of crossings is the codimension C, so the sign is determined by kind of how far away it is from being minimal of the associated Grothendieck polynomials that lacing diagram. And the sum is over K lacing diagrams. So you can't take like all just crazy ways of drawing lacing diagrams, and then you have to find these specific K lacing diagrams. But again, it's fairly computable, because once you find a minimal one, you just have these moves you can apply. And this was conjectured in 2004 by Luca Romani, who have many interesting formulas of their own for these. Paper in Journal of Algebraic Geometry. And I have set 7 minutes. And so that's our formula, and this is like open for a while, so I thought it was a very fun thing to try to prove. How did I get interested in trying to prove this? Well, I'll give you some idea of the ingredients, but not in any kind of detail. The main one was previous work of mine with of just Radschott and myself. We use several ingredients of this, like basically a connection of orbit closures with Schubert varieties. And so this is a new connection, new connection, arbitrary orientation of these orbit closures with Schubert varieties that have been instrumental in the equity-oriented case. There's some formulas like this for quivers where all the orientation, all the arrows are going the same direction, so we just want to apply our work to answer this conjecture. Reduction to the bipartite setting. So I made my example bipartite. It works for any orientation type A. Oh. I hope I said at some point I'm working with type A quiver. Oh, that's the only place the lacing diagrams make sense. Yeah. Reduction to bipartite type A. An interesting thing here. This reduction and reducing this, so reducing kind of the geometry of orbit closures to the bipartite case, you can kind of do it in a pretty natural way. The fact that this behaves with respect to K-polynomials really is some interesting facts, such as the fact that these orbit closures are Cohen-Macaulay, which was proved by Bobinsky and Swara in 2002 using representation theoretic methods and previous work of Lakshmi and Magyar. We proved it independently via our connection with Schubert varieties. It was interesting to see this Cohen-Macaulayness of orbit closures, which has been around for 15 years or something, being really instrumental to our formula. And what other ingredients we use? The main kind of technical thing, the main kind of technical thing is we use a kind of simultaneous Grosvenor degeneration, what I'll call it, my terminology. So one way to study varieties of coordinate rings is via Grosvenor degeneration. So here we have a group acting on our orbit closure, this base change group acting on the orbit closure. So at the same time, we degenerate the thing we're studying to a product of these matrix Schubert varieties. It's really actually a union of products of matrix Schubert varieties. We're also degenerating the base change group, sorry, I'm getting myself enough room here, to a product of kind of, what do you call this, fiber products of upper and lower triangular matrices over T. So anyways, I didn't want to give a lot of detail here, but we degenerate both the thing we're studying and the group action on it on the same time in a situation that's better understood. And then we have to do some and then this gives us some knowledge. Maybe the interesting thing to remark here, is this is really where the lacing diagrams appear naturally. This is a union of products of matrix Schubert varieties, and here the minimal lacing diagrams index the irreducible components. So this is what I meant when I said at the very beginning that these lacing diagrams appear naturally as a geometry, is that when you make this Grosvenor degeneration to matrix Schubert varieties, there's exactly one irreducible component for each minimal lacing diagram. And that's even itself, not so easy to see. And unfortunately, that's not enough to really get K-polynomials. This will give you something slightly easier, which is called the equivariant cohomology class. And you can get it from this way of doing it. To get the K-polynomials, you need a little bit more. You need some kind of K-theoretic Mobius inversion. This is due to Knudsen. And this is where these K-theoretic diagrams come in. They're a little maybe less natural from the representation, or less obvious that they would be useful from the representation theory side. Those come from kind of doing any kind of inclusion-exclusion process on these irreducible components. These end up being special points of lower strata. And this allows us to basically get this formula. There's a ton of combinatorics, which I don't even want to start trying to write all the different combinatorial tools we use on there. I'll throw out a few words for the interested parties. We use like Foamy and Kirilov's pseudo-line arrangements that they use to come up with formulas for double Grothendieck polynomials. These are re-encoded by Bergeron and Billy as RC graphs, also known as pipe dreams, and by Knudsen and his co-authors. So we use lots of combinatorics of that. And yeah, I'll stop there. That's basically the ideas of the tools that go into the proof.
Okay, some questions? Mark? Yeah, please.
So this is all from type A quivers, as you said. Do you have any idea how to do the other quivers?
The question is, these are for type A quivers. Do you have any idea how to do the other quivers? I have lots of ideas and zero proofs. We do, I would say, inspired also by work of Bobinsky and Swara on type D. They know that the orbit closures in type D are Cohen-Macaulay and normal, and rather than singularities characteristic zero by making a connection with double Grossmannians, and they build off work of Michel Brion. So by putting this together, using his work and the Bobinsky-Swara work, they got these results on type B orbit closures. We're hoping to kind of use this and maybe look at the growth generation techniques there.
In what?
Type B is pretty wide open. I don't think there's a lot of results at all. Andras Lewin, so maybe here this week, he has some results in type B a little bit. And so yeah, lots of ideas, no proofs. That's exactly what we're working on right now.
Some lot of questions.